Hi guys, so in this tutorial we're going to be talking about Lewis structures in organic chemistry. When it comes to organic chemistry, the foundation of all molecules is its Lewis structure. The Lewis structure tells you exactly how the atoms in the molecule are connected. Now, if you've taken general chemistry, you would have had a lot of practice with many different kinds of Lewis structures, including polyatomic ions, radicals, and very few basic Lewis structures of organic molecules. So based on your knowledge of general chemistry, in organic chemistry, we're only going to focus on very few elements. And so you don't need to know the entire concept of Lewis structures in order to tackle Lewis structures in organic chemistry, because one, we're only dealing with a handful of elements, and two, these elements always follow the same patterns of connectivity between atoms. So the elements we're going to be dealing with are hydrogen, our halogens, fluorine, chlorine, bromine, and iodine. And then of course you can't have organic chemistry without the element carbon and the other elements in the second period that are most important are nitrogen and oxygen. So as you can see, we're only going to be dealing with about 8 elements in all of organic chemistry. From time to time, we're also going to see a little bit of phosphorus and a little bit of sulfur, but these are very far and few in between. Our main focus is going to be, again, hydrogen, fluorine, chlorine, bromine, iodine, carbon, nitrogen, and oxygen. So the bonding patterns of these elements are always going to be the same. Hydrogen and all of our halogens are always going to make a single covalent bond. So these elements very few times, or almost never, will ever make double or triple covalent bonds. They will always be single bonds. Carbon, which is in group 4, is going to make 4 covalent bonds all of the time. Now there are going to be exceptions to this, which we'll get to later on, but for the time being, carbon always makes 4 covalent bonds. Nitrogen will always make 3 covalent bonds. And in general, it will always have 1 lone pair. Oxygen will have, or always make, 2 covalent bonds. And it will always have 2 lone pairs. And then phosphorus, which falls under the category of nitrogen in the periodic table, will practically be identical to nitrogen. Because they are in the same group, they share similar chemical properties, and so they also share similar bonding connectivities. And sulfur, being in group 6 under oxygen, will also follow almost identical patterns to oxygen. In order to demonstrate why these bonding patterns exist for these elements, what we have to really go back to is we have to go back to what is known as the Lewis dot symbol, which is the basis or the foundation for how we build Lewis structures. So the Lewis dot symbol is basically a way to symbolize an element and its valence electrons. Which I'm just going to symbolize with E negative. So we also have to go back a little bit to our periodic table and remember where or how we deduce the number of valence electrons for any given element based on its position in the periodic table. So if we go to hydrogen, hydrogen is over here in group number 1 or 1A. And so based on the group number, using this methodology of numbering, this will tell you how many valence electrons elements in this group have. So hydrogen being in group 1 will always have 1 valence electron. If we move on and skip over to the other elements in the second period, the nonmetals anyway, boron, carbon, nitrogen, oxygen, and fluorine. Boron is in group 3A, carbon is in group 4A, nitrogen is in group 5A, oxygen 6A, and fluorine 7A. So just like with hydrogen, the numbers that correspond to the group number also correspond to the number of valence electrons. So boron and all the elements underneath, including aluminum and so forth, will all have 3 valence electrons. Silicon under carbon will be the same, and all the elements below this. As I said before, phosphorus is under nitrogen, sulfur is under oxygen, and your other halogens in group 7 are all the same. So how do we symbolize these? Well, since we know how many valence electron each element has, the way that these electrons or valence electrons are symbolized are by a dot. So this dot here symbolizes the valence electron of hydrogen. Since hydrogen only has 1, we write 1 dot next to hydrogen. It really doesn't matter where you place it, but we usually place it to the right of the element. For the element boron, we're going to want to spread these electrons out as best as possible. So we usually place 1 electron on each side of the element's symbol. For carbon, we're going to do the same thing. We're going to spread the electrons around, so 1 on each side. Now when we get to phosphorus, it's going to look like carbon initially. So we're going to have 4 electrons spread out as best as possible. And now our 5th electron is going to end up being paired. Again, it doesn't matter where you actually put the pair, but I usually put them on the top. For sulfur, we're going to have 1 more electron, so that means it's going to look like phosphorus. But now we're going to have an extra electron, and therefore we're going to have to pair another set of electrons. And then, of course, for fluorine and all the other halogens, we're going to need to pair 1 more set of electrons to give us our 7. Okay, so these are the Lewis dot symbols which we would use to build molecules for Lewis structures. Now, what you must remember from general chemistry is that for covalent bonding, For covalent bonding, the valence electrons are shared. So what this means is that whenever two elements come together to form a covalent bond, each electron, or each element rather, must bring one electron to share. So based on the Lewis dot symbols, the number of single electrons that are not paired is what is going to tell you how many covalent bonds that element can possibly make. So for boron, which has 3 electrons, which are all individual, none of these exist as a pair, boron can make 3 covalent bonds. Carbon can make 4 covalent bonds, as we saw. Phosphorus and nitrogen can only make 3. Even though we have 5 electrons, these two on top are paired, so they're not available for bonding. And so this is why nitrogen can usually only make 3 bonding or share 3 electrons with 3 other atoms. Sulfur can only bond to 2 other elements, the same as oxygen, because it only has 2 electrons to share. And fluorine can only make 1 bond as well, just like the other halogens. When it comes to Lewis structures in organic chemistry, there's a concept that we're going to need to tackle, which you may have been introduced to in general chemistry, called formal charge. This is a calculation of an atom's or an element's charge in a given molecule. And there's a formula for this formula charge in typical general chemistry books, which is sort of a bit complicated, and I like to always simplify it. So for me, this formal charge is going to be equal to the group number of the element that we're interested in minus the number of atoms attached, or the number of atoms bonded, and then also minus the number of electrons as lone pairs. But we count these electrons individually, not as actual pairs. Okay, so we'll do some very simple examples of very simple Lewis structures so that you can see how these formulas work. So the first thing we'll do is very simple. We'll do ammonia, which has this Lewis structure. We can do also carbon dioxide, which has this generic Lewis structure. And we'll do one more, boron tetrafluoride, or BF4 minus, which is a ion which carries a negative charge. And of course we have to draw in all the lone pairs. So formal charges are calculated for individual elements in a molecule. So each element in the structure has its own formal charge. So we're going to do nitrogen and hydrogen for ammonia. So formal charge, I just abbreviate as FC, and you'll also see it abbreviated that way in many books. So the formal charge for nitrogen, so we remember the group number for nitrogen is 5. The number of atoms bonded to nitrogen is 3 from the 3 hydrogens. And the number of electrons as lone pairs is equal to 2. So 5 minus 3 minus 2 equals 0. So the nitrogen in ammonia has a charge or a formal charge of 0. The formal charge for hydrogen, hydrogen is in group 1. It is bonded to only one other element, which is nitrogen, and there are 0 lone pairs, or 0 electrons as lone pairs. So this formal charge is also 0. We're going to continue doing this. So the formal charge for carbon and carbon dioxide, the group number is 4. The number of atoms bonded is 2. And the number... So in organic chemistry, there is a concept that you may or may not have been introduced to, the concept known as formal charge. So this is the calculation of an element's charge, positive or negative, that may or may not exist in a molecule. So there's a formula for this that is relatively complicated in many books. I've simplified it down. So to me, this formal charge calculation always works, and the group number comes first. So the element's group number minus the number of bonds that the element is making, minus the number of electrons as lone pairs. And these electrons are counted individually, not as pairs themselves. So we're going to do some examples. The first example is going to be our just very basic ammonia molecule, very simple. Then we can do carbon dioxide. And lastly, we can do an ion such as boron tetrafluoride, Bf4-, which has this Lewis structure. Of course, we're going to include lone pairs. So sometimes we can also use lines instead of pairs of dots. If we have to make too many dots as lone pairs, we can use these lines that also symbolize electron pairs. So if we calculate the formal charge for elements, so we have to do these individually for whatever element you're asked for in a given molecule. So for nitrogen here in ammonia, we're going to do, its group number is 5, and the number of bonds that it's making is 3, and the number of electrons as lone pairs is equal to 2. So 5 minus 3 minus 2 is equal to 0. So the nitrogen atom has a 0 formal charge, which means that it is neutral. For hydrogen, we can do the exact same calculation. The formal charge, the group number for hydrogen is 1. The number of bonds it's making is 1, and the number of electrons as lone pairs is 0. So this also comes out to 0. So what this tells us about the ammonia molecule is that none of the atoms have a charge. It is a neutral molecule because all the atoms have a charge of 0. If we do this for carbon dioxide, and we calculate the formal charges for carbon and oxygen respectively, Carbon is in group number 4. Carbon is making 4 bonds, and there are 0 electrons as lone pairs. So this is 0. Oxygen is in group number 6. Each oxygen is making 2 bonds, so it doesn't matter which oxygen you do this for. And there are 4 electrons as lone pairs. So again, this will come out to be equal to 0. And again, this tells us the same thing. It tells us that the carbon dioxide molecule is a neutral molecule, at least in this Lewis structure. We're going to see later on, through the concept of resonance, that there are different ways to draw the structure for carbon dioxide. So now, for boron tetrafluoride, which has a negative charge, because a negative charge is indicated, one of the 2 elements that we calculate the formal charge for is going to have to be, or come out to be, negatively charged. So for boron, we have group number 3, 4 bonds, and 0 electrons as lone pairs. This comes out to be -1. And for fluorine, we are in group 7. We have 1 bond, and we have 6 electrons as lone pairs. This comes out to 0. So in general chemistry, for ions of this type, we usually wrote them in brackets and wrote the negative or the positive charge on the outside, without actually indicating which element was the one that carried the negative charge. Now that you have been introduced to formal charge, if we were to be really specific about where the negative charge actually is, we would write that negative charge right next to the boron to indicate that that boron has a negative charge. Now, if we think about this conceptually, what does this actually mean in terms of the bonding for boron? Well, you have to remember that when we have a negative charge somewhere, that means that we have gained electrons from somewhere. Since the boron is making 4 covalent bonds, 1 to each fluorine, from the Lewis dot symbol of boron, boron only really has 3 valence electrons of its own, which means that the 1 extra electron that boron has, which gives it its negative charge, is the electron that came from the fluorine, or one of the fluorines in BF4. So this 1 extra electron that the boron is sharing with the fluorine is what gives boron its negative charge. Alright, so this concludes this video on the very basic foundations of Lewis structures and formal charges as it applies to organic chemistry. Please hit that like and subscribe button for more tutorials on organic chemistry.